Okay, so the master exams, all the scores for master exam attempt 2 will be completed and posted by 5 p.m. today. And then I'm going to send out an announcement with those who didn't pass what you need to do. Okay, so that'll be all set by 5. Look for an email or a Blackboard announcement. Just in a nutshell, you're going to have to come find me now. So if you did not pass both times, then you're going to come and do it in my office hours. Okay, that's the brief version. Okay. Let's see, where am I going here? Okay, so we had this example last time. We were looking at this function g of x, and we were investigating all the values of the function and both of its derivatives at these x values. And we came up with this table. So I want to look particularly, let's look at this at x equals 0.5. What is happening to the accumulation at x equals 0.5 based on these numbers? 1.3, 125, 0, and 9. So just kind of think about doing this problem again. If you have notes, don't go look at your notes to figure it out, but think about it again. What can we conclude? What's happening there to the accumulation at x equals 0.5? Take 30 seconds to talk about it. So what's happening at 0.5? Okay, so what is the first derivative equal to 0 tell us about the accumulation? If the first derivative is 0, then what can we deduce about the accumulation? Pausing, what does that mean, pausing? Constant, right? That the output of the accumulation, or that accumulating quantity, isn't changing for a moment. So we say that's pausing. Okay? And then what does it mean that the second derivative is positive? Well, we just talked about this. So for the accumulation, what does it mean? What does it mean for the accumulation if the second derivative is positive? This was your top hat. Concave up. It means that the rate of change is doing what? The rate of change is increasing. And there's two ways that the rate of change can increase. It can get less negative or more positive, right? So on the left side, the rate of change is getting less negative. That's increasing rate of change. On the right side, the rate of change is getting more positive. That's increasing rate of change. Okay? And so that gives us this concave up shape to the accumulation graph. So where along there is the accumulation pausing? Right at the lowest point. Right there is where this pause in the accumulation is. Because here the accumulation is decreasing and here it's increasing. So for one moment at the bottom, it stays constant. So this kind of information then helps us to see. So we could say that in this accumulation function, we have what's called a local. In the local area, it's a minimum. And so these numbers are telling that story, right? These numbers that the first derivative is 0 and the second derivative is positive. We put that together and we say, oh, there must be a low point of the accumulation. It must be hitting what we call a local minimum. Okay, so what would need to be true at a local maximum? So the accumulation graph looks like that. So what would the numbers be doing, telling us, or what would the numbers be like to tell us that we have a local maximum of the accumulation. Talk to the person next to you. Go. And then find an x value. Find one of the x values in the table that has a local maximum. Find an x value in the table that has a local maximum. Okay, first derivative at local maximum. First derivative would equal, or be, 0, because also at a local maximum you have a pause, right? The accumulation is not changing for a moment. Its rate of change is 0. So first derivative, 0. What about second derivative? Less than 0, negative, right? Because the second derivative, so the rate of change is decreasing the whole way, right? Getting less positive, more negative, means the rate of change is decreasing, and so its derivative would be negative. So which x value is a local maximum? Yeah, the silence is, this is the right answer, right? None of them, okay? None of those are a local maximum because they don't fit this profile of a first derivative of 0 and a second derivative less than 0. Okay, so let's summarize, let's see, some terminology here. So critical value. So what we're talking about now is what's called critical value. The critical value of a function f is any value of x where, first of all, the function has to exist, okay? So that's kind of obvious. So this is the obvious statement, but you have to have a valid output to your function, and then one of two things could be true. Either the first derivative is 0, that's what we talked about, or if that first derivative doesn't exist, that's another way that you have what's called a critical value, okay? So first derivative is 0, or the first derivative doesn't exist, at a place where the function, the accumulation truly exists, then you have what's called a critical value. That the x value is the critical value.
What do you mean by like does not exist? You mean like
Yeah, we'll talk about it in a second. So let's focus first on the these are the ones we'll see more of, is where the first derivative is 0. Okay? So we've said this. Then the function f, its output, stops or pauses momentarily, increasing or decreasing at c. So it was increasing or it was decreasing, and then for a moment, the accumulation doesn't change. And then after that, it's increasing or decreasing again. Okay? Except for the trivial case of a constant function, right? Of course, the first derivative is 0 if the function is just constant, right? That's the kind of a trivial case. So we're talking about functions where we're increasing and decreasing, and at for a moment in time, the output stays the same. And so this is what we mean by a critical value. Okay? So does this guarantee a minimum or a maximum value? We talked about that our minimums and maximum values have a first derivative of 0. Does it guarantee it? Does it guarantee it? All right, well, let's think about x cubed. What's the derivative of x cubed? 3x squared. At 0, they would have a critical point because the derivative is 0. So, what do you remember what x cubed looks like? Okay, so we have a critical point at 0 because the accumulation pauses. But that's not a local max or local min. Okay, so a local max or min occurs at a critical value, but having the first derivative be 0 does not guarantee that you have a local max or min. There's other things that can happen, like this, right? What's happening here? So it's pausing, but it's increasing. It pauses, and then it keeps increasing. So then, what condition guarantees a local max or min when that first derivative is 0? So we need more information, right? and we need more information than just that the first derivative is 0 to have a local max or min. So here's example. You see there's one local max there, one local min. So at 0.42, so the critical value is the x value where the critical point occurs. So the x value of 0.42 is a critical value, and the x value of 1.58 is a critical value. And these particular critical values give a first derivative of 0. They are defined and are 0. Okay? Each is a local extremum. So that first one, what else would we need to know besides the fact that the first derivative is 0 to know that it's a local maximum?
The rate before and after.
The rate before and after. What about it?
The sign of the rate before and after.
Okay, so you're saying that the rate of change before is
Positive.
positive, the function's going up, and then
Negative.
afterwards is negative. Yeah. Good. Okay, so yes, the first derivative changes sign. Over there, the first derivative is positive, and then 0 for a moment, but then positive again. So it's increasing, pause, increasing. But at a local maximum, you're going to have increasing accumulation, or positive first derivative, and then you're going to have the pause, and then you're going to have decreasing accumulation, or negative first derivative. So the first derivative changes sign at both of those places. At the minimum, it changes from, the first derivative changes from negative to positive. What's another way that we could, so that's one way to say, yes, we have a local max or a local min if the first derivative changes sign. What's another way to know if we have a local max or local min? What we just talked about on the previous slide. Remember
The second derivative.
what about the second derivative? So what about the second derivative at a local max? Is it 0? No, its rate of change is decreasing. Therefore, negative. And at the local min, rate of change is increasing the whole way. Okay, so second derivative will tell us the second derivative is not equal to 0, and it can confirm whether we have a local max or a local min. What about the second derivative on that x cubed graph? It is 0, right? It's 0. So yeah, the accumulation pauses, but then we have an inflection point, which creates increasing to increasing or decreasing to decreasing. Okay, so the second derivative, just to summarize, second derivative greater than 0 means the first derivative is doing what? The second derivative is greater than 0. No, that means the first derivative is increasing. And we have a local min. Local min. So if the first derivative is increasing with the first... Sorry. The first derivative is increasing and 0, that means the second derivative is positive, we have a local min. And then similarly, if the second derivative is less than 0, that means the first derivative is decreasing. And we have a local max. Okay, so just having, the moral of the story is just having the first derivative equal to 0 does not guarantee a local max or local min. You need something else. Either you need to look at the first derivative on either side and see that it changes sign, or you need to look at the second derivative and see that it's either positive or negative. And either of those things will confirm what exactly you have at that critical value. Okay, so then the other way that you could have a critical value is if the first derivative is undefined. DNE, does not exist. So you can say undefined or does not exist. And so there are two situations where you can have the first derivative the function exists, but the derivative does not. Anybody know what one of those is? Yeah, so he's showing a corner point. Okay, corner point is like, there it is. So here's the graph of x to the 2/3. X to the 2/3 has a corner point at x equals 0. And so I'm showing here rate of change values. So here the rate of change, this is the rate of change because, x to the 2/3 would be 2/3 x to the negative 1/3 would be its rate of change function. So I'm showing that there. And so what's the rate of change doing here? For x greater than 0, what does the rate of change do? I'll start over here. Ready? Rate of change is? Decreasing, decreasing. Getting less positive. Okay? Back here, what's the rate of change doing? Increasing or decreasing rate? Decreasing, getting more negative. Okay, so we get more and more and more negative, but then what happens at 0? What's the rate of change at that corner point? What would you say? What's the rate of change there? Well, coming from the left, it sure looks like it's going to a large negative value. Looking at it from the right, it sure looks like it's going to be a large positive value. Right? So it doesn't pause, it just jumps, right? It jumps from a high negative to a high positive. So if we actually put it on 0, what does graphing calculator do? It says does not exist, right? So this is one way it does not exist. It's like it's saying infinity. It's trying to make sense of this, okay? But at that corner, the rate of change does not exist because here it's decreasing to a very high negative, and then all of a sudden it jumps to a high positive. Okay, so and notice what do we have there at that point? What do we have? And the accumulation function has a local minimum. Okay, so it is a critical point, and it's a local minimum. Okay, the other place where you could have, other situation where you could have a function value defined, but the derivative does not exist, is if the graph is momentarily vertical. Momentarily vertical. So something like this. I'll try to draw it. So like increasing, where's my pen? Says it's on. Here's my beautiful kids. Trying to figure out how to turn the pen on. Still not working. Okay, I'll draw on the board. Here we go. So it's like increasing concave up. And then just for a moment, it's vertical. And then it keeps increasing concave down. That would be the idea of the function value exists, but the first derivative does not exist. And that's a critical point. That is a critical point. Okay. So let's kind of put this together with an example here. So I have this function j of x. It's an accumulation function. So I'm going to determine numerically if j has any relative maxes or mins or inflection points. So we could put this in graphing calculator and do this all graphically. We could trace on the graph and look for the high points and low points. But we want to kind of practice using the mathematics we're learning. So we're not going to use a graph to determine anything. Rather, we're going to use a numerical analysis, kind of a symbolic treatment of this, in order to make these conclusions about do we have local maxes, local mins, inflection points, etc. Okay? So, oh, but I sure need my pen now. Let me try turning it on and off. All right, so write the function down. And so, while I'm trying to get my pen to work, see what kind of progress you can make. you're trying to figure out where there might be a local max or a local min. So what does that mean for you in terms of solving algebraically? It's got to go, or it's just bored or something. Okay. So what's true at a relative max or relative min? What is true? Right. We're looking for critical values. That's critical values. And that is where, we just said, we're looking for first derivative to be or undefined. So if we're looking for relative maxes, or sorry, I should say local maxes or mins, I like that better. But just know if you ever see relative max, relative min, that means the same thing. Local max, local min, we'll use local. I think local is more descriptive. Let's talk about in the local area. Okay? So if we need to find local maxes or mins, we know that those occur at critical values. So what are we going to do? Yeah, we're going to take the derivative. All right, we're going to take the derivative. So we're going to take j prime of x. Hopefully it's an easy one. We get negative 15. It's 18x minus 3x squared. And we're looking for local max or min. So we're looking for critical points. So we will do, what will we do? Yeah, we want to know, we want values of x that will make this 0, make the derivative 0. That's what we're saying. Those are critical points, potential local maxes and mins. So we're going to have 0 equals. And now, so now we've got to, let's rearrange this here. How do we figure out values of x that are equal to 0? Yeah, so let's see if you remember from your algebra days, first of all, we can factor out a minus 3, because all of it has 3. And then remember, if it's rigged, right? So we're hoping it's rigged. And if it's rigged, then it's two binomials multiplied together. What is it? So they need to multiply to plus 5 and add to minus 6. Minus 5, minus 1. Is that right? Agree? Therefore, what x values make our first derivative 0? Or in other words, are critical values of this function j? X equals 5 and 1. How do we know what's going on at 5 and 1 without the graph? So let's start with x equals 5. How can we figure out more specifically what kind of critical value we have? So we need to figure out, do we have a clause where it's like x cubed, where it's going to keep increasing or keep decreasing, or is it going to be a local max or a local min? How do we know? Okay, so he's saying there's one thing you could do. You could take a number a little bit less than that and a little bit greater than that and look at what function. Okay, so we could look at the first derivative, and we could look at something. We said that if it's a local max, the first derivative will change from what to what? First derivative. No, not increasing to decreasing. Positive to negative. Okay, so we could take 4.9 and 5.1, put them in the derivative, and see if it changes sign. If it changes sign, then we have either a local max or a local min, depending. What was the other thing we could do? Second derivative tells us stuff. So let's do the second derivative. Let's go back to this one. Second derivative is minus 6x Okay. So, second derivative at 5. Is what? Negative 6 times 5 plus 18 equals negative 12. What does it tell us? Second derivative is negative, so what about the accumulation? J is? J is what at x equals 5 if the second derivative is negative? Concave down. The rate of change is decreasing, so it's concave down. So we have first derivative 0 at 5 and concave down. Therefore, at x equals 5, local maximum. Okay, what about x equals 1? Second derivative equals? Find that what is positive or negative. Negative 6 times 1 plus 18 equals? Positive 12. So J is? Okay, so if this is easy for you and you just want to hang out and chat, don't do that because there's people around you who's never done this before. It's very distracting to them. Okay? So if you're whispering about the problem, that's fine. But don't tune out and distract people around you. Okay, so J is what? Concave up. All right, so concave up and first derivative 0 means? First derivative 0 and concave up. Local min. So we have a local max at 5, local min at 1. Okay, are there any inflection points? Remember, inflection points mathematically means that? Remember what we said, inflection points, last time. You had some in your homework. Second derivative is? Undefined? 0. So if we set the second derivative equal to 0, we get x equals 3. So at x equals 3, we have an inflection point. Meaning what? Meaning that so what is this talking about? How is this talking about the first derivative? Saying the first derivative is pausing for a moment. First derivative is pausing for a moment. So it's either changing from increasing to decreasing or decreasing to increasing. It's pausing, all right, the first derivative. Okay, so we have an inflection point at 3. We have concave down at minus 12, concave up at 12. So let's just make a rough, just based on what we've done so far, let's make a rough sketch. Everyone, I'll leave you to have this information written down. I won't be able to remember all of it, but I need to give myself some space. So can I erase? Am I good? Okay. Question?
Yeah, so why does a negative value make J concave down? Why does it positive make it concave?
Because if the second derivative is negative, then the first derivative is decreasing. So the rate of change then is getting less positive or more negative. And you see the shape of that? Less positive rate, more negative rate. So your accumulation is doing that. Yeah. Other questions? Yeah?
Is the inflection only for the second derivative?
If the second derivative is 0, so that's when you have an inflection point.
Is that so? Is the first derivative constant?
So let's what's going on? So if you put 3 into the first derivative, what do you get? So at x equals 3, what's the first derivative? Let's figure that out. It's a good question. Okay, so at x equals 3, what is the value of the first derivative? Negative 27. This is negative 27 plus 54 minus 15. What's that? 12? 12. Okay, so at x equals 3, the first derivative is 12. So what does that tell us? We have an inflection point, and the first derivative is 12. So what's happening to the accumulation at x equals 3? Increasing, decreasing, or staying constant?
Constant.
Nope, the first derivative is positive. It's going up. It's going up, and we have an inflection point. So it's heading up, but the rate of change is changing from, we'll have to, it must be changing from increasing to decreasing at that moment. So the rate of change pauses for a moment at 12. It's heading up at 12, pausing for a moment, increasing up to 12, and then starts decreasing down from 12. But let's kind of sketch. Let's put all this together kind of with a sketch, and that will help make more sense of it. Can I erase now? Okay, so we had x equals 1, x equals 3, and x equals 5. Is that right? And at 1, we had local, what was it? Local min. At x equals 3, inflection. And the rate of change was? Okay. And here we have a local max. So just a very rough sketch here. There's other details we could fill in, but we won't for time's sake. So at x equals 1, we know we're hitting a low point. Well, we could plug 1 in here and get the actual value too. But that's fine. So maybe it's here. But so we don't know what height this is at, right? We'd have to actually plug 1 into this. All right, and then at x equals 5, local max, so I'll just put it up here, who knows? And then x equals 3, we said that it's heading up at 12, but then it's an inflection point, so the rate of change changes from increasing, then the rate of change is pausing, and then it's changing to decreasing. Okay, so here is the general shape of this graph. I don't know where it is up and down. It could all be positive, it could all be negative. We could find that out by just plugging in x1, plugging in some x values into j to get a height for it. But the general shape of it is like this. Local min, then inflection with an increasing accumulation or a positive rate, and then a local max at 5. And so we could throw that in graphing calculator. What was the function?
Minus 15x.
Minus 15x. 2 minus 15x
Plus 9x squared.
plus 9x squared.
Minus 6.
X cubed. That's it? Okay? Actually, my sketch was pretty good. This was negative and this was positive. So there's that local min. At 3, there's our inflection with a rate of change of 12. And then there's our local max. Questions on this example? Using the numbers to make conclusions about how the accumulation is behaving.
So ideally, with this method, we could draw on graph.
No, well,
Specifically,
I mean this is an easy polynomial. Yeah, but the idea is that numerically you can make lots of conclusions about the shapes of graphs with this.
you know, when you would like reach a limit in terms of being able to draw a graph using this method.
In all different directions. There's so many different kinds of functions involving so many kinds of arithmetic kind of computations that that's not a linear question. Like, you know what I mean? Like, functions there's so many different kinds of functions, and some of them can be analyzed this way. So that's the shortest answer I could do. Okay, so let's do next here. So let's look at an example of how this plays. So this idea that we can find, where is internet? This idea that we can determine Okay, we can determine where a function, accumulation function, hits a local high point or low point. And that's what we call optimization. So in a real world setting, we want to know when the accumulation reaches the highest point, like if it's profit, or usually we want the highest profit, or we want the most of something, right? We want the biggest volume or something like that. Or we want to minimize something, like we want to minimize cost. So we can use these techniques, these numerical techniques, into what's called optimization. So here's an example of that. Let me spell it right. Optimization. Means, so we've got some real world quantities we want to know. When do we have the most of that? Or when do we have the least? Because that's important to us. We want to try to get the most, or we want the least, okay? So here we have the top and bottom margins of a poster are 6 centimeters. So they're telling us this is 6. And the side margins are 2. So these are 2. And they say the printed material has a fixed area. So this region in here is fixed at 382 square centimeters. And we want to find the dimensions of the smallest possible poster. I want the smallest possible poster. Okay, so here's this is the thing that I'm going to, this is going to be my mantra, this is going to be the chorus that I keep singing, just until you get it. With optimization problems, the centerpiece of these problems is a function whose output is the quantity to maximize or minimize write it down, star it. Everything you do in setting up these problems is about getting this, a function whose output is the quantity we're trying to maximize or minimize. Why do we want that? It's everything we've just did in class. What are we going to do with that function then? To figure out how to maximize or minimize it. Take its derivative and set equal to 0. Because we know if we have a pause, where the first derivative is 0, we get pauses at high points and low points. So everything we do in setting up these problems, there's going to be all different varieties, all different kinds of geometry, and all kinds of topics that these problems are about. But the central element is if you're trying to maximize or minimize something, you need a function whose output is the quantity you're trying to maximize or minimize. So we're going to need, in this case, we're going to need a function of what? Area of what? No. Find the dimensions of the poster with the smallest area. So we want a function whose output is the poster's area. Okay? So we want a function, so we'll call it a function. And that this will be the poster's area. The printed material is fixed. That's not changing, right? That's always going to be 382 no matter how we set up the poster. But what changes as we mess with the dimensions here is then the area of the resulting poster, the whole thing. The whole thing. Okay, so that's going to be our goal. So what do we know? We know that, let's call this the height. Let's call this little h. Little h is for the printed material. And little w for the printed material. So we know that h times w equals 382. Okay, so now we can get a formula for the area of the whole poster. So the area of the whole poster would be like, what? Big W, call it big W, times big H. So but it's going to have to be in terms of these dimensions that we've said here, h and w. So what is going to be the area of the whole poster in terms of little h and little w? So what is big W? W plus 4, right? So width is going to be the width of the printed material plus 2 here and plus 2 here. And what's going to be the height of the whole little h plus 12. So we've got something like a function for the poster's area, but what's still not complete about it? Okay, it's in terms of two different changing quantities. All right, so when you get this function whose output is the quantity you're trying to maximize or minimize, you need to get it down to one input variable. How can we get this a function? So it's either going to be w or h. Take your pick. So we can do a of w. How are we going to get this thing only in terms of w and not w and h? Yeah, so we have this relationship between h and w here. So it would be w plus 4. If this center thing is fixed at 382, then what does little h have to be? 382 divided by w is h. Any questions so far? Okay, so we got it. So this is the centerpiece of the problem. The function whose output quantity is the quantity we're trying to maximize or minimize. In this case, what are we trying to do with the area? Minimize. We want the least poster material, right? Because that's going to cost the least. But we still need this to be 382, and so that this ensures that. This function ensures that the printed material will be 382. But there's different ways we can configure that, right? And so this is taking all those into consideration. So how are we going to get the minimum value of the a function? All right, so we're going to look for a local minimum. How do we get a local minimum? Derivative equal to 0. Okay, so you could do the product rule on this, or you could multiply this out first and do it term by term. Okay, so let's do that. Let's multiply it out. So I'm going to rewrite AW down here. It's going to be 382 plus 4 times 382 over W plus 12W plus 48. See what I did? So I just rewrote our function, and now I want the rate of change of that, or the derivative of that. So derivative of 382 is 0. So this is like W to the minus 1, right? So it's going to be negative 4 times 382, W to the minus 2, or over W squared, plus derivative 12. And so we want to set this thing equal to 0. So the hard part's over. So we're just trying to find the value of W that makes the first derivative 0, or we're going to get a pause. So now it's just arithmetic. You just got to know your algebra, how to solve this for W. Okay, I wanted to finish the example that I was doing at the end of class on Wednesday so that you could see the full solution. I kind of talked it through, but it's kind of hard to follow. So let's just review it. It says the top and bottom margins of a poster are 6 centimeters, and the side margins are 2 centimeters. The area of the printed material is fixed at 382 square centimeters. We want to find the dimensions of the poster with the smallest area. And so, like the related rates problem, it's really important that you define quantities. So I'm going to actually write these out. I didn't do this, but this is really important. Little w is the width of printed material. We want units for that. Little h is the height of printed material in centimeters. And then I call big W the width
of the poster in centimeters, and big H, the height of the poster in centimeters. Okay, and so we made some progress. We said that therefore little h times little w is the 382 fixed value. And the area of the poster then would be little w plus 4 times little h plus 12. And that was our area of the poster, but we said that we need that in one variable, one independent or input variable. We decided to make that w, so we needed some way to write h in terms of w, and that comes from this fixed relationship here. So what does h equal? H equals 382 divided by w, so I can substitute it in, and that gives us the area of the total poster as a function of w. And we said we wanted to minimize this quantity area, and so to find a minimum, we know that we will, local minimums are where the first derivative equals 0, or at a critical point, critical value. So we take that first derivative and set equal to 0. And down here, that's not there. So I had this area function. Before I had it as 382 plus 4 times 382 over w plus 12w plus 4 times 12 is 48. So I just expanded that formula right there into 4 terms, and from that we said that to get the minimum we're going to look for local minimums of this function, which means we need critical values which come from the first derivative being 0. So the first derivative, here's the first derivative right here. I use the power rule on this. This is w to the minus 1, so it would be minus 4 times 382 over w squared plus 12, which is the derivative of 12w, and we're going to set that equal to 0. So that's where I left off. So let's go ahead and solve this. So to solve this, I can move the 12 over to the other side. That'll be negative 12, but then I'll have a negative here, so it'll be 4 times 382 equals positive 12. So I subtracted 12 from both sides, and I multiplied both sides by negative 1. And then we could think about cross-multiplying to get rid of this w squared in the numerator. So that would be w squared 12, w squared equals 4 times 382. And so then w would be the square root of 4 times 382 all over 12, or square root of 382 over 3. Now all that tells us that, so this is a critical value. But we saw that there's different types of critical values. Local min, local max, and then there's ones that are neither max nor min, like x cubed, like the x cubed graph. So we needed to confirm that this is truly going to give us a local minimum, and we can do that with the second derivative. So the second derivative, taking the derivative of this right here, would be the second derivative. And this is like w to the minus 2. So I'm going to have minus 2 times minus 4 times 382, which is actually positive 2 times positive 4, 382, all over w cubed. And the derivative of 12 is 0. So here's my second derivative. So let's here. And we have to confirm that at this value of w, this thing is positive. So we can just see that by observation. This is a positive expression for any positive w value. So if w is positive, when you cube it, it'll be positive, and this whole thing will be positive. So clearly, just by observation, when we put the critical value into the second derivative, we're definitely going to get a positive value. And that is now what confirms local min. Okay? You may have to, in other problems, observation might not, you may not be able to just observe it. You may have to actually take that value, plug it in, and figure out whether it's positive or negative. But here it's very easy to see that that positive w will give a positive second derivative. So we do have a local min. So what did we find? We found little w. So going back to this, little w is the width of the printed material. It's this quantity here. This is why it's so crucial to define your variables at the beginning, so that after we do all this math, we get a number, we know what that number means. This number means the width of the printed material in centimeters. What do we need? We want the full dimensions, W and H, of the poster. So we see the big W was just little w plus 4. We have it right there. So we can come over here. So you can do the square root of 382 divided by 3. And so this is this value of w, and that's little w, right? So again, emphasizing why do we define those at the beginning, so we know what we're dealing with. 382 little w is the width of the printed material on the inside of the poster. So that's 11.3, and that's centimeters. And let's keep track of where that came from. Again, that's a 382 over 3. Okay, the big W then would be 11.3 plus the margin, the 2 margin over here, and the 2 margin over here, so we're going to add 4. So it's going to be 15.3. Okay, so that would be, again, as an exact expression, radical 382 over 3 plus 4. In terms of web work, so this answer 15.3, some of you encountered, it might not be enough decimal places. And so right now I have graphing calculator set at 3 significant figures. We could change that and show more. But here's a foolproof thing you can do in WebWork. Just enter this in WebWork. That's an exact value. It'll be the calculator for you. You never have to worry about how many decimal places you put in. So this could be your WebWork entry. But now, if you're talking to somebody about designing this poster, you're not going to talk in terms like this. You're going to say, we need to make this poster 15.3 centimeters wide. Okay, so that's why you need both. Little h can come from this relationship here. If we know little w, little h is determined. So it's going to be 382 little h, 382 divided by little w. Here's little w, so we're going to do 382 divided by that. So I'll cut. Do 382 divided by paste, and so we get a little w value of 33.9. Okay, and so for big H, it's going to be that thing plus a 6 for the top margin, 6 for the bottom, or 12. It looks like 45.9 centimeters. Again, exact value would be plus, so that expression there, up here, for our big H dimension in WebWork. Okay, I hope this helps with the homework for Friday.